Hello everyone. So today we will solve problems on Newmarks method. Okay, we'll continue the previous class. Okay, we'll solve few more problems on Newmarks method today. So today's class we will be solving a problem where the beam is having varied moment of inertia. So in such case, how to continue we will discuss today. Okay. So let us have the problem now. So a simply supported beam of variable moment of inertia is loaded partially with uniformly distributed load. As shown in the figure. Determine the maximum slope and deflection in the beam using 6 nodal points and Newmarks method. Okay, so this is the problem, and the figure given is like this. Okay, what do you do? We'll have two columns. Let us divide the given page into 2 columns. Okay, this one, and here we'll have space for this is for figure, this side, this is for calculations. Okay, the given figure is like this. There is a beam with varying cross section. Okay, that's nothing but moment of inertia is varied across the length, right? So this is the beam, and as it is simply supported. Okay, and the load is actually there in the so it has divided into 3 portions, and loading is there in the first, second and third division. Okay, so this is the UDL, which is nothing but W kilonewton per meter, and so the total length is L actually. So consider that as L, and so here this is divided into 6 portions. Okay, it is divided into 6 portions. Let us consider each as H. Okay, each length as interval as H. Now, so step 1, we need to divide the given beam into number of divisions. Actually, in the problem itself, they have mentioned that it is divided into 6 divisions. So step 1, dividing the beam. Okay, so here the beam is divided into 6 elements as shown now. Okay, as usual, there is a load in this. So this is divided, the beam is divided into 6 parts. Okay, 0, 1, 2, 3, 4, 5 and 6. So 6 spans, 1, 2, 3, 4, 5, 6, but the nodal points have started from 0, 1, 2, 3. And this is W, kilonewton per meter, and we know that you need to demarcate the W values. Okay, so usually in the inverse method, so we will take this as W0, W1, W2 like that. So W0 is 0 and here W1 is equal to W, okay, and W2 is equal to W, W3 is equal to W, and W4 here, okay, W4 is equal to 0, W5 is also equal to 0, and W6 is equal to 0. Okay, so those are the values. Next, step 2, we need to calculate the equivalent concentrated loads. Okay, so in this equivalent case, so equivalent concentrated loads, we need to first assume what are those loads, and we should calculate later. So we'll have the beam again, we'll draw the beam again. So, but in the exam you can just draw one figure and you can represent in everything in one figure. But why I am drawing here is to for the understanding purpose. Okay. So here is the beam, and this is divided into 6 parts. So the loads P1, the loads are given by. So here you will have P naught. Okay. And here you will have P1, and this is P2, P3 here, P4, P5 and P6 at the end, right? So these are the loads, and the UDL is there in this region. Okay, 0, 1, 2, 3, 4, 5 and 6. Okay, so these are the loads, equivalent concentrated loads. Now let us calculate the equivalent concentrated loads. So that is step 3. So in step 3 we have to calculate the equivalent concentrated loads. Equivalent concentrated loads. And we know for UDL, so if we have a UDL as the load, so equivalent concentrated loads are given by the formula, that's nothing but H by 6 into 2W naught plus W1, that is the formula, right? And that is end load, and intermediate loads are given by H by 6 into W naught plus W1, 4W1 plus W2, right? So that is the formula. But now see here, it starts from it is the, okay, so we have the formula given by, so P naught is equal to H by 6, okay, into 2W naught plus W1, okay, and intermediate loads are given by H is equal to H by 6 into W naught plus 4W1 plus W2. Okay, so this formula is applicable whenever the UDL starts immediately. So it has to start from this end. Then if this is W0, so these formulas will apply. But in our problem, there is no UDL. So the formula will be applicable from the point of UDL. Okay, it starts from here. So the load values will come from here. The formula, these formulas will be applicable from here. Okay, so this P0 will become P1. Okay, and this will become P2. Okay, whereas here these values will become 2W1 and W2, and here W1, W2 and W3. And so it's very clear. Since the UDL starts here, so the load calculation will also start here. So the remaining portion, wherever there is no load, they will be directly written as 0. So in our case now, so P0 is equal to 0. Okay, directly, and then P1 is equal to, so since the load is starting here, so you will have the value. Okay, so P1 is equal to, formula you can write h by 6 into 2W1, that's nothing but the end ordinate, so end ordinate plus the next ordinate. Okay, so that's nothing but W2. So because P, and in case of P0 actually there is no load both the sides, so definitely it is 0. But whereas in the case of P1 there is the load on this right hand side, there is no load on the left hand side. So the calculation starts from here. Therefore P1 is equal to h by 6 into 2W1 plus W2. So substitute all those values, you will get so h by 6 into 2 into W. So W1 is W and W2 is also equal to W. Therefore this will become, P1 will become, so 3W divided by 6, so it will become 0.5 H WH, right? So this is the P1 value. Next P2, let us calculate P2. So P2, here you have load on this side as well as this side, so P2 is equal to h by 6 into W1 plus 4 times W2 plus W3. This is the formula, because that become intermediate load. Okay, so that's nothing but h by 6 into W plus 4W. Okay, 4 times W plus W. So this will become 6W by W, I mean 6W by 6. So 6 cancel, so it will become WH. Therefore P2 is equal to W into H. And we all know that all these loads are acting downwards, so they will be negative. So this will also be negative, this will also be negative, therefore minus 0.5 WH, and this will become minus WH. Okay, P2. Next P3. So P3 is equal to, and P3 will become end concentrated load for this UDL. So that end load will be obtained by the same formula. Okay, so the first formula, so minus h by 6 into 2 times the end load W3 plus 1 time the previous UDL, I mean intensity, that's nothing but W2. So that will become minus 6 by h by 6 into 2 times W plus W. So P3 will also become minus 0.5 WH. Okay, so this is how we need to calculate the P3. Next, what is P4? P4, because there is no load on this side as well as this side, P4 will become 0. Similarly, P5 will also be equal to 0, and P6 will also be equal to 0. Right? So hence these are all equal to 0. Hence you have only P1, P2 and P3 values. Okay, so that completes the calculation of equivalent loads. Now let us calculate the bending moment and shear forces by using Newmarks table. So we will have to have these values, and with the Newmarks table you can simply calculate the bending moments and shear forces. So remember, P1 is 0.5, P2 is 1 time WH, and P3 is 0.5 WH. Okay, so let us draw or prepare the Newmarks table. So step 4, calculation of bending moment and shear force. Step 4, calculation of shear force and bending moment using Newmarks table. Okay, so now in this case, let us prepare a Newmarks table having first row for nodal points. Okay, and you will have a first column for the particulars, and you will have one more column for writing the designations. Okay, and then starts the nodal points. Okay, so here we will have 7 points. Okay, that's nothing but 0. It starts from here, so 0, and we will be dividing this into 6 portions. Okay, just some roughly we will have. I am not drawing thick lines, just construction lines, so that we will have neat writings. So 0, 1, 2, 3, 4, 5 and 6 nodal points. So these are the nodal points, okay? Nodal points. And here you will have the multiplier. Here is multiplier. Okay, multiplier. So yeah, let's start. Load, equivalent load. Okay, so equivalent load in bracket, equivalent load P, so which is equal to, at 0 P0 is 0, P1 is minus 0.5. So here the multiplier is, you can write WH for all the values, multiplier is WH. So minus 0.5 and here minus 1.0, P2 is 1.0, P3 is minus 0.5, okay? And then P4 is 0, P5 is 0, P6 is 0, right? So that's how you can write down. Next, trial shear, okay? So as usual, we should calculate the trial shear. Trial shear is obtained by the formula, okay? I mean, trial shear, you in the beginning you have to assume some shear force, okay? And you with that you can go on calculating. So in our case, in order to assume the trial shear, so what we will do, definitely it's a trial one. We cannot have an exact value. So actually speaking, you can calculate exact value if you apply the formula. And in the last class, I had shown you how how a trial shear can be assumed, and which will be simpler than calculating the exact answer. So you can assume any value. Okay, some any value you can assume here in the trial as the trial shear, and you can continue, so that if there is error, that error can be rectified later and eliminated. Okay, so now let us see. So how to assume the trial shear, because you know the half load, because of this some part of the load will come this side and some part will go to this side. So we'll assume that the P1 and P2 total load will come to this side. So that trial shear will become this plus this, which is nothing but what is the value we have? We have 0.5 and 1. So P1 and P2 value will transfer this side. Actually speaking, we don't know how much exactly it's coming this side. So some part will go this side and some part. So let us assume 0.5 and plus 1.5, 1. So that's nothing but 1.5 as the trial shear. Okay, there is no rule here actually. So you can assume some, approximately this particular part will come this side. That way we can assume, right? Yeah, okay. So now with this value, let us start with the trial shear. So trial shear V is equal to, here that's nothing but P1 plus P2. P1 plus P2 is minus 1.5. Therefore, the trial shear is 1.5. And 1.5 is because this is acting upwards, okay? Shear force will be acting upwards, so positive. So plus 1.5 you can consider. Now with this plus 1.5, so we need to calculate the next shear force. So next shear force at the center here will be obtained by 1.5 plus 0, that will become 1.5. Okay. Next shear force at point number 1, over here, will be obtained by 1.5 minus 0.5, that will become plus 1. Okay. Then sorry, not this one. Okay, here the center in between this portion. So 1.5 minus 0.5, it will become 1, right? Next, so if the shear force for the between the region 2 and 3, between the point 2 and 3, it will be equal to 1 minus 1, 0. Next, between the 3 and 4, it will be obtained by 0 minus 0.5, minus 0.5. Next, minus 0.5, 0. So that will be minus 0.5. Again, this will be minus 0.5 in the end region, and at the support also minus 0.5 it will become, and the multiplier is WH only, because this is same shear force. So it is minus WH. This is the trial shear. So here we don't know whether this trial shear is correct or not. So that we can check when we calculate the bending moment. Okay. Next, so trial bending moment. So trial bending moment M you can obtain just like this. So we'll have so in the beginning we need to assume a trial value. Trial value starts from the boundary condition, and we know here in case of beam, because it's a simply supported, the trial shear will be exactly equal to 0 only. So we can assume exactly. Okay, so that by using the boundary conditions. Okay, so here the bending moment is given by 0 trial bending moment, right? With this trial bending moment, next bending moment at different points can be obtained by adding the previous bending with the next shear force. Okay, so previous bending moment is 0, so next shear force is 1.5. So add that, and that you will be writing over here at point number 1. So that's nothing but 1.5, and the multiplier is, so W H will be there into H, you will have to do it. So WH square will be the multiplier. So 1.5 WH square. So next bending moment will be 1.5 plus 1, that will be written at the next point. So that's nothing but 2.5 WH square. Next 2.50, that will become 2.5 only. Next 2.5 minus 0.5, that will become plus 2 WH square. Next 2 minus 0.5, again that will become 2 minus 0.5, 1.5. Okay. Next 1.5 minus 0.5, the last bending moment will become plus 1.0. Okay. So you need to stop over here. There won't be any another kind of force, calculation. There won't be anything like that. Okay. In shear force, you need to end at the support, whereas here this exactly ends at the support only, last point only. So no need to further calculation. So this is the last bending moment which is there, and we know in case, and here it is, if you see here, because it is a simple support. Okay, this is simple support. Definitely the bending moment will not be any value. It will be 0 only. It has to be 0. But in our case, what is the value you got? Actually, it is 1. Okay, so 1. Actually, it should be 0. So that means there is a error. This is the error. Okay, so this is the error, and this error has to be distributed and rectified, and actual value of the bending moment shear forces has to be calculated. Okay, so therefore error is equal to this is the error. Therefore correction we need to calculate. Okay, so correction for each point, because this has to be distributed for 6 points, therefore correction is equal to, so since the error is positive, the correction will be negative. So minus 1.0 divided by 6 divisions. So the value will be equal to minus 0.16666, you will get it, but I'll round it off to 0.167. Okay, so the error is, correction is correction for shear. Okay, this is correction for shear. So correction for shear is minus 1 divided by 6. Okay, that's nothing but minus 0.167. Now let us have this as a separate thing. Now let us calculate the correct shear force and correct bending moment. Okay, so correct shear. Okay, the correct shear can be calculated by V is equal to same thing. Thing is, because there are 6 regions, so there will be 6 corrections. So whatever the correct shear force can be calculated by just subtracting or this correction with the actual shear force values. Okay, so 1.5 minus 1.5 minus 0.167. That will give you actual value 1.5 minus 0.167. Okay, so that's nothing but 1.33. Okay, so 1.33, you write it down here. 1.333 is actual shear force, and even at this point also 1.333 will be the shear force. Next, 1 minus 0.167. Okay, so that will be equal to 0.8333. Okay, 833. Next, the next value is 0. 0 means point minus. Okay, 0 minus 0.167, it will become minus 0.167. Minus 0.5 minus 0.167, it will become minus 0.667. And again here same thing, okay, applicable here, minus 0.667, and even here also minus 0.667, and at the support as well minus 667. Okay, so that is corrected shear force or correct shear force. Next, correct bending moment. So correct bending moment, it's repetition of the previous procedure. That's it. No, nothing to be done here. So correct bending moment will be nothing but you start from 0. Okay, so as usual, and the next bending moment over here will be nothing but sum of the previous bending moment and next shear force. Okay, which is nothing but 0 plus 1.33. So 1.33 is the bending moment. Next, the bending moment will be nothing but previous bending moment plus next shear, which is nothing but 0.833. So 1.833 plus 0.833. 1.333 plus 0.833. So which is equal to 2.166. Okay, 2.166. And then you just consider this. Okay, so this will actually becomes 2.2 exactly, because 0.167 and 0.166 almost same. Therefore, this will become 2.0 exactly. And then minus 2 minus 0.667. 2 minus 0.667. So which is equal to 1.33 only. You will get it. Okay, so 1.333. So that will be written here. Okay, plus 1.333. And then 1.333 minus 0.667, so that will become 0.6667 only. Okay, 0.667, because almost double value. And minus plus 0.167 minus 0.167, that will become 0. Okay, so this is the exact values, and you can see here there is no error, and the multiplier will be WH here and WH square, which will be there over here. Okay, so this is how we will have to calculate the correct bending moment and the correct shear force. Okay, so this is same as the previous problem, but what is different here is it starts now. Okay, so you need the bending MIA diagram will be different, because and in this problem they have given different cross section. So this is 2I and this is I. So when you draw M by I diagram, you should divide 2 here and you should divide 1 here. And what are the differences? I let you know now. Okay, I'll let you know. But we'll see how in this figure itself we will calculate, in this table itself we will calculate M by EI values here. Okay, so M by EI calculations, M by EI. So it is 0 here, and this is M by 2, because here you have 2 values. Okay, divided 2I is the I for this region. From 0 to 3 it is 2I, from 3 to 6 it is 1I. So therefore 1.33 divided by 2 means 0.667. I'll write it 0.6667 by EI. So multiplier we will write here. Okay, so WH square is actual M, so 1.333 WH square divided by EI will be the EI value, because I have divided 2 here, so already it is divided by 2. So now 2.167 divided by 2 means 1.083 will be M by EI, and multiplied by WH square by EI. And here at point number 3, so you can see here, you can observe at point number 3, there are 2 I values. Which one to be taken? So we will not be knowing. So we will have to calculate both the values, and whenever necessary we can use this, and whenever necessary you can use the other value. Okay, so consider that. Here this is 2 divided by 2, 1 this side. So we will divide it into 2 portions. So this side and this side. So left hand side it will be 2 divided by 2, it will be 1, okay, 1.0 WH square by EI, and the right hand side 2 divided by 1, 2.0 WH square by EI. So there are 2 M by EI values at this point number 3. Next at 4, 1 point, because we divided by 1.3, 1 only, EI, 1 EI, so 1.33 EI, and this is also 0.667 EI, and this is 0 EI. So these are the M by EI values, and we will make use of these values for calculating the slope and deflection. Okay. Okay, now let us continue with this M by EI values, and we'll make use of this M by EI diagram. And this M by EI values will be considered as load acting on the beam. Okay, and considering that as load, calculation of shear force will be given, will give you slope, and calculation of the bending moment due to that M by EI diagram will give you deflection. Okay, so that is what we will be doing now. So finding the next step number 6, calculation of bend, slope and deflection. Okay, next step, calculation of slope and deflection. Calculation of slope and deflection. So now what we have to do, as I have already told you, consider M by EI diagram as load on the beam. Okay, then shear force will give you slope, and bending moment will give you deflection. Okay, that's what we need to do. It's just a repetition of the previous step, but the thing is, since in the previous case the load was UDL, so the equivalent concentrated load, we have, for calculation of equivalent concentrated load, we have used different formula. Now we will be using different formula, and that's all the difference. The remaining thing is entirely it is same, whereas the load here it will be little complex. Okay, that's all the difference. Okay, now what we will do, we will divide this portion into, as I told you, for calculation purpose, divide this page into 2 portions. Okay, we'll have to have more space for right hand side, because the formula will be lengthy. Okay, and so now what we need to do is, we need to consider M by EI diagram as the load acting on the beam. Consider the beam supports. Okay, and now here, so M by EI values have to be considered over here. So divide the given beam. So this is 0, 1, 2, 3, 4, 5 and 6. Okay, now what is the moment at point number 1? So moment at point number 1 is 0.667 1.083, 1 to 1.33, 0.67. Just remember. So the ordinate over here is 0.667. Okay, 0 here, 0.667 here, 0.667. Okay. Next, you have 1.08 at point number 2, 1.08 over here, 1.083. Okay, and then 1 here, right? And then immediately it increases to 2. And then at point number 4, it is 1.33. Okay, 1.33 will be here, somewhere here. And then 0.667 over here, and 0 will be here. So we'll just join them, come like this, and here it will be a straight line. And again, because it's a WH square, so it will be parabolic. The bending moment will be parabolic. So here this value is 1.0, and this value will be 2.0, and this value is 1.333 WH square, and this over here it will be 0.667 WH square by EI. Okay, and here it will be 0. Therefore, the multiplier here for this diagram is given by WH square by EI, M by EI diagram, isn't it? Right? So this is the loading acting on the simply supported beam. Okay. Now considering this as a load, what we need to do is we need to calculate the shear force and bending moment. Okay, that will give you slope and deflection. So to start with, so we need to calculate the equivalent loads. So in order to calculate equivalent load, there is one difference which is there in this case of two different EI values. This is 2I and this is I. So what we need to do is you need to split this portion into two beams, okay, and having different two loads, okay, because what's happening here is the problem, while calculating P will be when you are calculating maybe P3. So which one to be considered is a question mark. Will it be this be W3 or this be W3 is a question mark. So to solve the problem, so what we will be doing, we will be splitting this beam into two imaginary beams, this beam and this beam, and what you have to consider is, so separately you have to calculate the loads considering them as two different beams. Okay, so just you will understand now. Okay, in such cases, in such case of different loads, in such case, okay, consider above beam into two beams. Consider the above beam into two beams. Okay, so above beam into two beams as below. Okay, as below we will write and calculate the equivalent load separately. Calculate P separately. Okay, separately we have to calculate it. So here you split this beam into two beams. So I'm actually for convenience, for convenience I'm writing this one. In the exam you can avoid this step. I mean this drawing you can directly write over there only. In the above figure only you can write. So this is one beam part. The other part you have this is another beam, another part. So as usual you represent this diagram here. Okay, So here it is 2. Draw parabola. So you have support here, one support here. So this is 0.667 and here 1.083 and here 1, whereas here it is 2.0 and here 1.333 and here 0.667. Okay, so with these values now let us continue the calculation of the loads. Okay, so for calculation of the loads, so there will be the equivalent loads like this, okay, which will be this way. You will have the equivalent load like this. So support, there will be support, one support here, another support. So here this will be P naught, okay, P naught will be there as usual, and this is P1, okay, because this is 1, 2, and here there are 2 points. So 3, what we will do, we'll assume this is 3 left and the third point right, okay, 3R, and this will become 4 and this is 0.5 and this is 6. Therefore P1, P2 and this load will be P3L left, okay, and this is P3 right, P3 right. That's all the difference. So you'll be having 2 loads actually. So P4, P5 and P6. Okay. So therefore the total load over here. So what actually you need to do is, for calculation purpose, you split this into 2 parts. First calculate P3 left, considering this is the end load, okay, using different formula, and similarly this also will become end load. So you'll be considering both the end loads, okay. Otherwise, if you have considered both together, there will be a confusion which to be considered as W3. So now W3, there will be 2 values, okay. W3L will be there and W3R will be there, okay, whereas this is W0, W1, W2, W3 left, W3 right, W4, W5 and W6 will be 0, okay. Now let us start calculating the equivalent loads, right. So P naught will be given by the formula, because it's not a straight load, okay, it's straight line variation, it's not linear variation, it's a parabolic variation. For parabolic variation, the formula for the equivalent load is given by h by 24 into 7W0 plus 6W1 plus minus W2. This is negative, minus W2 will be the formula. And just go on substituting and go on calculating the equivalent loads, and then we can calculate the slope and deflection. So h by 24 into 7 times W0 is 0 plus 6 times W1 is 0.667, okay, minus the W2 is 1.083, okay, and the multiplier here will be actually as usual WH square by EI will be there as usual. Okay, because this is the load only, WH square by EI. Okay, therefore P naught you will get it equal to, if you simplify and if you calculate it, you will get the value of this is equal to 0.122 W. So in this, the H into H, WH cube will become, so WH cube by EI, this is the P naught value. Okay. And since it is acting downwards, so negative, minus 0.122 WH square. Next P1 is given by, because that's an intermediate value, okay, so the intermediate value can be calculated by a different formula, okay, so which is given by P1 will be given by P1 is equal to H by 12 into W0 plus 10 W1 plus W3, okay. And here, because we are calculating the left hand side, so it has to be considered as W3L. Okay, W3L. There is no confusion now. Okay, we have split into two beams, right? So W3L, and substitute the value WH by 12, and this is negative. Okay, so minus H by 12 into W0 is 0 plus 10 times W1 is 1.083. Okay, 1.083 here also. And then plus W3, that's nothing but 1.0. Okay, if you simplify, and as usual, there will be a multiplier WH square by EI, which will be there. Therefore, P1 will become, if upon the substitution and simplification, the value of P1 will become, P1 is equal to minus 0.65 WH cube divided by EI. Okay, so that is the value. P1 value. Next, P2 for P2 again, because it's also an intermediate load, so the same formula is applicable, minus H by 12, but terms will be different. W1 plus 10 times W2, because this is P2, therefore W2 will be in the middle, plus W1, W2, W3. Sorry. Here it is. It's W2. Okay. In P1, this is W2. W2 is. Okay. I'm sorry. This is 0.67. Okay. 0.667. W0. Yeah. 0.667, and this is 1.083. I'm sorry. Okay. So that will be there, but the actual value, whatever answer you are getting, it is correct only. Here it will be W3L. Okay, H by 12 W1 plus 10 W2 minus plus W3L. So upon the substitution, minus H by 12, W1 is 0.667 plus 10 times 1.083 plus 1 times because the W3L is 1.0. Okay. And into WH square by EI. Therefore, the value of P2 will get it as minus 1.04 W upon substitution and simplification, H cube by EI. This is the value of P2. Now P3 will be obtained by, P3 will be equal to P3L plus P3R. Okay, you will have two values, right? So considering these are separate beams, you need to calculate P3, okay, adding these together. Therefore, now P3 will be equal to, you just obtain that, P3 is equal to H by 24 into 7W, now P3, this side will be equal to W3, because this is the end load, okay, so end load will be obtained by 7W3L, okay, plus previous value, that is nothing but plus 6 times the previous value, that's nothing but W2, 6W2, minus again previous one, minus W1, okay, plus one more value will be there, okay, overall it will be negative, okay, minus H by 24, okay, because it's acting, total load is acting downwards, so that's why. H by 24, again here the end load is this, so therefore 7 times W3R, okay, W3R plus the next value W4, 6 times W4 minus W5, okay, this is the formula, right? So upon substitution, let us, P3 will be equal to minus H by, so negative sign I'll take it outside, H by 24, okay, 7 times the W3L is 1 times 0, 1.0, and 6 into W2 is 1.083, and minus W1 is 0.667, okay, plus this negative sign I have kept it outside, therefore H by 24, okay, that also would have taken outside, so 7 times W3 right, 2.0, plus 6 times W4, 1.33, minus W5, 0.667, close the bracket, and once again close the bracket. So after simplification calculation, we'll get P3 is equal to minus 1.43 WH cube by EI. So this is the value of W3, P3 you should consider. Similarly, we should calculate P4 and P5, P6, okay. So P4, the value of P4 is given by P4 is equal to H by 12 into W3R plus 10 W4 plus W5, okay, which is obtained by H by 12 into W3R is 2 plus 10 times 1.33, okay, plus 0.667, okay, W5 is 0.667. Therefore, P4 you will get it equal to minus final value will get it equal to 1.33 minus 1.33 WH cube by EI. Okay, this is the value. Next P5, similarly P5 is equal to same formula. This is also an intermediate load P5. Okay, P5 is an intermediate load, so H by 12 only. So the formula is given by P5 W4 1 time W4 plus 10 times W5 plus W6, okay, H by 12. So which is given by H by 12 into W4 is 1.33, okay, plus 10 times W5 0.667 plus W6 is 0, and the value of P5 you will get it equal to minus 0.67 WH cube by EI. Okay, so this is the value of P5. The last value P6. Okay, P6 you can get it by the formula because it's an end load. Okay, P6 will be the end load, so we'll have to use H by 24 formula. So H by 24 you can consider as negative. Okay, H by 24 my into the last that's nothing but W6, 7 W6, okay, plus 6 W5 minus W4. This is the formula. So minus H by 24 into 7 times W6 0 plus 6 times W5 is 0.667 minus 1.333 W4. So the value of P6 you will get it equal to 0.111 WH cube by EI. Okay, so these are the concentrated loads, equivalent concentrated loads which you will be getting. Now what we will be doing, so we will use the Newmarks table and find out slope and deflection. Okay, slope and deflection we will calculate now. So for calculating the slope and deflection, now let us draw the Newmarks table. Next I will consider the Newmarks table. Nodal points. This is nodal points for nodal points, and okay, and divide. Yeah. So you will have particulars here and designations here. Okay, and then I will have 1, 2, 3, 4, 5, 6 and multiplier. Okay, so this is nodal points. Okay, and here designation will be there as usual. Okay, then here the point starts. Okay, so 0, 1, 2, 3, 4, 5, 6 and this is multiplier. Right, now load, equivalent loads you can write down here. So we have all the values. I just remember I have these values. I'll keep writing here. So P naught is equal to the value here is minus 0.66 minus 0.122. Okay, and multiplier is WH cube by EI. Remaining values I'll be just writing as usual. Minus 0.65, minus 1.04, then minus 1.43 P3, P4 is minus 1.33. You need not write this negative sign also, you can just continue that way only. Okay, and W6 is P6 is minus 0.111. Minus 0.111. Okay, WH cube by EI. So whatever lines I have drawn, these are only for construction purpose. Okay, now so trial slope. We should consider the trial slope. For finding the trial slope, what you can do is you can consider the total, some trial value. Okay, so what we will do is we will consider this plus this plus this. Okay, how do you calculate the slope in the moment area method? Moment area method, the slope is nothing but the area of the M by I diagram, right? So in this case, you can see here. In this case, the slope on this side will be equal to total area, half area. Okay, it's nothing but reaction. Okay, reaction over here. So what we can do, we can consider adding this P1, P0, P1, P2 and P3 up to P3L we can add. So we will assume that as support reaction which is coming over here on the left hand side. What are the values? 1.22. Yeah, let us calculate 0.122 plus 0.65 plus 1.04 and then plus okay, maybe some part of it. Okay, 1.43 we'll assume. 1.43 if we add, actually speaking, some half of that it will come. So it is equal to almost 3.24. So actually speaking, okay, so that is the trial value. But what we do for convenience purpose, we'll assume 3. So instead of 3.24, anyhow it's a trial value, right? So we'll assume 3, so that simple to write and all. Therefore we'll have a three value, trial value like this. Okay, you understood, right? Because I know this is the only part you need to put your mind. Okay, so thing is, whatever load is there on the left hand side, half of the portion, that load approximately you consider as the slope on the trial slope on the left hand side, summation of all that. Okay, so now we will assume 3 as the slope, and we know clockwise slope will be considered as negative here. So minus, add them all. So minus, if you add them all the values, so minus 3 will be assumed as the trial slope. Okay, so now 3 goes like this, 3 and then actually what you can consider is 3 and so what you need to, you just consider this as positive only, because as I've already told you, if you can consider negative also, but then it will be 3 minus the difference of that you should consider. Otherwise here it will be summation. Okay, so if you consider negative also, no problem. If you consider negative here, this will be this minus this, so it will be the actual value. So 3 minus of minus plus. Okay, so 3 minus of minus 3 plus minus 3 plus 0.22 122, it will become a different value. So that is equal to, I will have the values. Okay, 3 minus 0.122, actually speaking, minus 3 minus of minus 0.122, which is equal to so 2.878. 878 will be the value. So that has to be written over here. So minus 2.878. Okay. Next. So for finding the slope between the point number 1 and 2, so it has to be then considered minus 2.876 minus of minus 0.67. That means plus it will become, okay, minus 2.878 plus 0.6 something. So I'll just write plus 0.65. It will give you minus 2.228 is the value, and then plus 1.04. Okay, plus 1.04 will give you minus 1.188. Okay, next minus 1.188 plus, that's it, minus of minus plus, it will become plus 1.43. it will become, this will become plus value now. Okay, plus 0.242, plus 0.242, and then plus 0.242 minus of minus, that will become plus. Okay, plus 1.33, right? So which will give you so 0.242 plus 1.33. Okay, that will be equal to 1.572 plus 1.572, and again the last value, last but one, so again plus 0.67, so 2.242. Then the support slope at the support will be given by plus 0.111, so which is equal to 2.353. okay, so the multiplier will be WH cube by EI only, WH cube by EI only. And now, so these are the trial values, but we don't know whether this value is correct or not. We don't know whether this value is correct or not. Okay, so this is how we can calculate. So just go on adding, minus of subtracting the values, you're going to get the values. Now we should calculate the trial bending moment, or trial deflection. We know that trial deflection at the simple support at the end will be definitely 0. So the trial deflection you can calculate, that's nothing but y is equal to 0 here in the beginning, and then the next deflection will be nothing but this deflection. Okay, this deflection plus the next this slope. Okay, so that's how you can calculate. So 0 minus of 0.28, so this will be minus 2.878. Again, next deflection at point number 2 will be nothing but previous deflection plus the next slope. Okay, so which is nothing but minus 2.878, right? Plus minus 2.228, which is equal to minus 5.16. okay, minus 5.106. Why negative sign? Because deflection is acting downwards. So the next one will be obtained by adding the next one. So minus of 1.1188. okay, minus 1.188, so which is equal to minus 6.294. it is increasing. Next it has to decrease. Okay, so plus 0.242. okay, so that will become minus 6.052. it's decreasing. Okay, here, and the next deflection will be plus 1.572. okay, and that's equal to minus 4.48. again, just subtract it and calculate the final deflection. That's nothing but minus 4.48 plus 2.242. So that has become minus 2.238. Okay, the multiplier is WH to the power 4 divided by EI. Okay, minus 2.238 is actual value. I mean, whatever you got. Is it correct? Is this correct? The deflection at the end support, it is having negative deflection. Definitely it cannot be, because it's a support. At support, the deflection will be always be 0. So we have to consider this as the error now. Okay, consider this as the error, and that has to be distributed in the slope. Okay, and then we should recalculate the deflection. Okay, therefore correction for slope is equal to, because error is negative, correction will be positive, 2.238, okay, divided by 6. Okay, and which will, as usual, WH to the power 4 by EA will be there as usual. Okay, so if we calculate that one, so 2.238 divided by 6, so each value will be equal to, the correction for the slope will be equal to 0.373. Okay, WH to the power 4 by EI will be there, and that will be default. So now let us calculate the corrected slope and deflection now. Okay, so for finding the correct slope and deflection, so let us continue. Correct slope now. So what we need to do, whatever previous values are there, so subtract that. I mean, you just add this to that one, adding our difference of that, whatever. Okay, so if the error is positive, you just add. If correction is positive, you just add. If correction is negative, you should subtract. Okay, so now the values will become different. Okay, so the correct slope phi will be equal to, or here first one will be equal to minus 3 plus 0.373, which is equal to minus 2.627. Okay, and another value will be here only, one more value will be here. Okay, which is equal to minus 2.8 minus 2.878 minus plus 0.373, which will be equal to 2.505. Okay, so which will be here, minus 2.505 will be here in between these values. Okay, this will be the support, this will be the actual shear. And now over here minus 2.228 plus 0.373 plus 2.373, it will become minus 1.855. Okay, minus 1.855 over here at between 1 and 2. So this is 1, 2, this is 0. Okay, so this will be how 3, 4, 5, 6. Okay, so next in between 1.88 next. So 1.888 minus 1.188 plus 0.373, the value will become minus 0.815. Okay, similarly, so the value plus so 0.242 plus 0.373, it will become 0.615. Okay, and then 1.52 1.572 plus 0.373, that will become 1.945, and then 2.242 plus 0.373, it will become 2.615. Okay, and then 3.373, it will become, actually that's not required, 2.726, this is not required for Bending calculation. Okay, anyhow, so these are the values. Okay, now correct deflection can be obtained very simple way. by how you calculate bending moment. Okay, so correct y, deflection y will be obtained by, so as usual, deflection at the correct trial shear at the end will be 0, definitely 0, start from 0, and this plus the next slope. Okay, so that will give you the deflection over here at point number 1. So minus 2.505. Next 2.505, then 1 point. So the deflection at the next point here will be equal to sum of these two. Okay, so therefore 2.505 plus 1.855, which will give you 4.36 is the answer. Next 4.36 actually negative. Okay, both are negative. So next plus this, okay, plus 0.815 will give you slope over here. Deflection at point number 3, which is nothing but 5.175. Okay, so now this is negative. This plus this will be reducing now. It will decrease. Okay, I'll just minus. So minus 0.615. It will become, okay, minus 4.56. Now this minus 4.56 minus 1.945, it will become, okay, minus 2.615. okay, minus 2.615, and now you can see minus 2.615 plus 2.615, it will become 0, and the multipliers are WH cube by EI here, okay, and WH cube by, WH to the power of 4 by EI here. Okay, so this is how we need to calculate the slope and deflections. Now what is the maximum deflection? So this is the maximum deflection. So therefore maximum deflection is equal to 5.175 WH to the power of 4 by EI. Okay, now in terms of L, if you wanted to calculate, so this is negative. Negative sign indicates downward deflection, does not matter, we can forget about that. Now let's substitute the L value here. H is equal to L by 6, right? So let us substitute and recalculate it. So minus 5.175, okay, W into L divided by 6 the whole to the power 4, okay, divided by EI. So if you substitute that, you will actually get 5.175 divided by 6 to the power 4, okay, 6 to the power 4, which is equal to 23 by 57. You can substitute this way instead of so minus 23 by 5760 W L to the power of 4 by EI. Okay, so this is the Y max for the given beam with partial deflection. Okay, you can cross check with this using some other methods. Okay, definitely it will be exactly this answer itself. Okay, so Newmarks method is a very nice method with trial bending moment, trial shear force, trial slope and trial deflection. Definitely we will end up with the exact answer. Okay, so this is how we need to calculate the bending moment, shear force, slope, deflection by using Newmarks method, even with in case of different moment of inertia. Okay, so that's the end of the class. Thank you, students. Bye.